In this video, we're going to learn about reaction mechanisms. We'll learn that many chemical reactions don't occur as a single step. Instead, they're going to occur as multiple steps, and we'll learn what the rate determining step is. So, reaction mechanisms mean that many reactions don't occur in a single step. Rather, they occur as a series of elementary steps. And the slowest step is the rate determining step, or the RDS. And that step will determine the rate at which the reaction will proceed. So if we look at our example, our first step here, we have two NO2s reacting to form NO3 and NO. This reaction is slow. In step 2, the NO3 and carbon monoxide react to form NO2 and carbon dioxide. This step is fast. But step 1 will be our rate determining step because it is the slowest. And the overall reaction rate is dependent on the rate determining step, which is the step that will have the highest activation energy. So if we looked at a graph showing the reaction mechanism, the one that has the highest activation energy will be the rate determining step and the slowest step. In most of the reaction mechanisms we'll come across, the first step is usually the slowest, so the rate determining step. So there are two rules that we must bear in mind. The first rule is that the elementary steps must add together to give us the overall balanced equation for the reaction. And the second one we're going to talk about more in our next video, but the mechanism must be consistent with the experimentally determined rate expression. And again, we'll talk about that in the next video. So let's look at the example we were talking about before. The overall balanced chemical equation is this one here. So NO2 plus CO makes NO plus CO2. Now we'll look at our two intermediate steps. So we need to cross off things that appear on either side of the reaction. So this can go, and so can this. And then our NO3s can go. And then what's left over is NO2 plus CO makes NO plus CO2. So this reaction mechanism works. Now, the NO3, which appears in both steps but not in the overall equation, is called a reaction intermediate. And we'll talk about intermediates a little bit later in this video. The term molecularity tells us the number of reactant particles that are found in the rate determining step. So a unimolecular would only have one reactant particle involved. Bimolecular, you would have two reactant particles involved. And termomolecular, you would have three reactant particles involved. We will use these to determine or develop the rate expression, which will be covered in our next video. So a unimolecular step would involve the decomposition or dissociation of a molecule into two or more smaller pieces. A bimolecular step would have two molecules colliding and reacting with each other. And a termomolecular step would have the collision of three different reactant particles. But that would have a very low probability of occurring because it would take more effort to react three at a time. So let's take a moment and examine a reaction mechanism that's been displayed graphically. So you'll see that we have our reactants, and then this looks familiar. This looks like the activation energy, but you'll see that there's a dip and then another rise again. So in each intermediate reaction, there's an activation energy that must be achieved. So as you go along here, these are your reactants. This is your transition state 1. That's where you would find your activated complex 1. And then there's a dip, and then there's another rise. So this is in transition state 2. This would be activated complex number 2. And then finally we produce our products. We can see that this reaction is exothermic because there is a release in energy. The products have less energy than the reactants. And you can see that the activation energy in the first step is higher than in the second step. So this would be the rate determining step because the activation energy is higher. And that would be an example of a reaction mechanism. This little dip here would be where your intermediate or intermediates would be found. So let's look at another example of reaction mechanism. So in this case, we actually have 3 transition states, so 2 intermediates. So we start off with HBr and O2. There is an activation energy. Again, this one's the highest, so this would be the rate determining step. It's the first step, usually is the first step. And then we have intermediate 1, and then another activation energy must be achieved to get intermediate 2, and then the third activation energy, then you produce your products. So we have 3 transition states to produce our products of water and bromine. So what do we do about catalysts? We know that catalysts increase the rate of a chemical reaction by providing an alternate pathway with a lower activation energy. Catalysts are not used up in the chemical reaction, so they're not considered a reactant or a product. However, they do appear in the rate determining step and in the intermediate steps. They just don't appear in the overall balanced chemical equation for the reaction. So now let's take a look at an example and we'll answer a few questions about it. So the first question is, which step is the rate determining step? And we can see here that the activation energy for the second step has a higher activation energy, so that would be the rate determining step. It's the slowest reaction. So how many intermediates are formed? So here's our reactants. We have 1 dip here, so each valley would be an example of an intermediate, so there is only 1 intermediate formed. Where do the activated complexes form? So this is the first transition state, this is the second, so these are where the activated complex 1 and activated complex 2 would be found, so at the peaks. What's the delta H of the reaction? So that's from here to here, so that is a difference of 100 kilojoules, and it's a drop, so it's exothermic, so it's negative 100 kilojoules. What's the delta H of step number 2? It goes from here to here, so that's about 140. And then the activation energy of step number 1 is 100 kilojoules. So you have to put in 100 kilojoules to allow that reaction to happen.